Okay, for Chemistry 1 today, you guys are going to be assigned some gas law problems, okay? We're going to use the combined gas law, which says that pressure 1 times volume 1 divided by temperature 1 is equal to pressure 2 times volume 2 divided by temperature 2. Now, pressures are going to be numbers that are assigned that have our units millimeters of mercury or torr or atmospheres or 101 kilopascals. And it's important that you have the pressures in the same unit. And so the pressure conversions that we were working on at the end of last class and finishing at the start of today's class are going to be important so that way we have like units for canceling. Volume got to be in the same units, and most commonly you're going to see it in milliliters or liters. You could possibly see it in cubic centimeters or cubic meters as well. Okay, remember also that 1 centimeter cubed is equal to 1 milliliter. Now, temperatures in gas laws need to be in the unit of Kelvin. Okay, and to get to Kelvin, it's the degrees Celsius plus 273. So let's say I had 10 degrees Celsius in a problem. If I want to know how many Kelvin is, I need to add 273, and I would have 283 Kelvin. And it's just Kelvin, it's not degrees Kelvin. Realistically, what the combined gas law does is it gives us an initial set of pressure, volume, or temperature conditions that the gas is under, and we're able to solve for a pressure or volume or temperature given condition changes. Okay, so maybe it heats up, or maybe the amount of pressure exerted on the gas has changed. And when working problems, you could be given a list of pressures, or you could be given them in word problems as well. Okay, and so if you're given word problems, we're going to want to list the variables out. And what I have here are 4 example problems that are listed as word problems, which are slightly more difficult than if I just listed pressures and volumes. So we want to make sure we show our work. So we're stating the equation, we're substituting into the equation, and we're finding our answer with the correct units, and we're showing the canceling of units. So here, my first problem that I have says that a gas has a pressure of 31 kilopascals. Now, at this point, it doesn't matter if I assign it as pressure 1 or pressure 2 because it's the first number I'm assigning. Most people use pressure 1 because it's the first number associated, and that is absolutely fine to do. So we know that pressure 1 is 31 kilopascals. Now, after that, it does matter based on what we're given in the problem and how the wording goes, because the gas is at that pressure is going to have a certain volume or a certain temperature, and we need to make sure that we're associating that as well. And so here, a gas has a pressure of 31 kilopascals and a volume of 2 milliliters. So 2 milliliters needs to be volume 1. Here, then it says, what will the pressure be? So I'm going to be looking for pressure 2 if the gas is allowed to expand to 30 milliliters. So we have volume 2, and that is 30 milliliters. Now, the problem doesn't mention temperature, and so it's safe to assume that temperature is remaining constant. So anytime we're dealing with the gas law problem and the problem doesn't mention it or directly states that a certain variable is remaining constant, then we're going to go ahead and just remove it from the equation. So even though my equation is pressure 1 times volume 1 over temperature 1 equals pressure 2 times volume 2 over temperature 2, I'm going to change that and just remove the volume or the temperature component because temperature wasn't mentioned and it's assumed to be constant. So here I'm going to deal with P1 times V1 equals P2 times V2. After I remove that variable, it's just substituting into the equation, and then from there, doing the algebraic steps in order to solve for our unknown variable. And so here, 31 kilopascals times my volume of 12 milliliters is equal to my unknown pressure 2 times volume 2 of 30 milliliters. And at this point, it's really become just an algebraic problem. So to isolate pressure 2, it's being multiplied by 30 milliliters, and I can just divide 30 milliliters to the other side of the equation. It eliminates it from the right side of the equation, and then I'm left with pressure 2 is equal to 31 kilopascals times 12 milliliters, all of that divided by 30 milliliters. Now, some people like to go ahead and solve for the product of 31 times 12, then divide 30 across, and that's fine too. I just prefer to do it this way so that I can see clearly that milliliters is on the top and bottom of my fraction, meaning that it cancels. So once I get that, I'm going to take 31, multiply it by 12, and then I'm going to, which equals 372, and then divide it by 30, and I get 12.4, and my unit is the only unit left in the problem, kilopascals. So we're going to put kPa, and this is how we solve these problems. So this first one was an example where temperature is held constant. Now, my second problem here says that if the temperature of a gas is 6 degrees Celsius, and so if I assign that to temperature 1, but I'm going to have to also then assign the and pressure of 740 milliliters to the pressure 1 as well, because those are the two initial conditions of the gas. Now, remember that temperatures need to be in Kelvin. So every time that we list out a variable, we should just automatically add 273 to it. And the reason that it needs to be in Kelvin is because Kelvin does not have a negative scale. The lowest number is 0 Kelvin, which is absolute zero. So we have no opportunity to have a negative outcome or negative volume or negative pressure in a gas law problem when we have it in Kelvin, which is the reason it must be in Kelvin. So it says, what pressure will the gas have at a temperature of 2 degrees Celsius? So my change is my 2 degrees Celsius. Remember, add 273 to get 275 Kelvin. And we're looking for pressure 2. Now, volume was not mentioned in the combined gas law, so instead of pressure 1 times volume 1 over temperature 1, we're going to have pressure 1 divided by temperature 1, and that equals pressure 2 divided by temperature 2. So we're then going to substitute into the equation, okay, where we have 740 millimeters of mercury divided by my temperature, 279 Kelvin, set that equal to pressure 2 divided by the changed temperature, 275 Kelvin. Again, at this point, it's really algebra, and pressure 2 is being divided by 275 Kelvin, so we're going to multiply the 275 Kelvin to the other side. That cancels over here, and then what I'm left with is that pressure 2 is equal to 275 Kelvin times 740 millimeters of mercury divided by 279 Kelvin. Again, Kelvin cancels with Kelvin, and I'm going to then be given 275 times 740 divided by 279, and I get 729.4, and my unit that's left, millimeters of mercury. Sorry, that kind of got a little scrunched up there. Now, my third example problem here, it says the volume of a balloon is 120 milliliters at 20 degrees Celsius. So I have volume 1 and temperature 1. Again, add 273 to your degrees Celsius every time to get to Kelvin. So we have 293 Kelvin. And it says, what will the temperature be? So I'm looking for T2 when the balloon is 0.5 liters. So V2 is 0.5 liters, and we're solving for temperature 2. Now, earlier I said that we had to make sure that we had like units, and this is just an example where I have volume 2 in liters and volume 1 in milliliters. And it does not change we don't have to change 1 to liters or 1 to milliliters. We just need to make sure they're both in the same unit. And so I'm just going to choose to convert my milliliters to liter. We know 1 liter is 1,000 milliliters. And so 120 divided by 1,000 gives me 0.120 liters. Now, we aren't mentioning pressure in the problem, and so we would have V1 over T1 equals V2 over T2. So if I plug into my equation 0.120 liters divided by my temperature, 293 Kelvin, and set that equal to 0.5 liters divided by temperature 2. Now, students often make an error here, and they try to just multiply the 0.5 liters across, which is the wrong thing, right? Because you're actually just solving for 1 over T2. So a little trick, let's go ahead and invert, or take the inverse of both sides. And so we're going to put 293 Kelvin on top and 0.120 liters on the bottom, and have that equal to T2 divided by 0.5 liters. So now, when I multiply my 0.5 liters across, I get the correct rearranging of the problem, 0.5 liters times 293 Kelvin divided by 0.120 liters. And so liters cancels with liters, and T2 is then going to be equal to 0.5 times 293 divided by 0.120, which gives me 1,220.8 in my unit, Kelvin. Unless the question asks for degrees Celsius, that's a perfectly acceptable unit to have. And it does seem like a rather large number, but we did have a rather large change in the volume of the gas. So the first 3 problems, I held one thing constant. In my last problem, I haven't left anything constant. I've only have one unknown from the combined gas law. So here we have a gas that takes up a volume of 17 liters at a pressure of 2.3 atmospheres with a temperature of 299 Kelvin. So my initial set of circumstances, volume 1, 17 liters, pressure 1, 2.3 atmospheres, and temperature 1 of 299 Kelvin. Then it says if I raise the temperature to 350 Kelvin, so temperature 2 is 350 Kelvin, and lower the pressure to 1.5 atmospheres, what's the new volume? So here I need to use the complete combined gas law. P1 times V1 over T1 equals P2 times V2 divided by T2. And I know everything but volume 2, so from there it just becomes algebra. So we're going to plug in 2.3 atmospheres times volume, 17 liters, divided by my temperature, 299 Kelvin. Set that equal to pressure 2, which is 1.5 atmospheres, times my unknown, volume 2, and divide it by 350 Kelvin. So from here, I need to isolate it. I'm first going to choose to move 350 to the other side. And so I would be then left with 1.5 atmospheres times volume 2 is equal to 350 Kelvin times 2.3 atmospheres times 17 liters, all divided by 299 Kelvin. Then, if I need to move 1.5 atmospheres to the other side, I'd be multiplying by 1 over 1.5 atmospheres, which essentially is just dividing the 1.5 to the other side, but multiply by 1 over 1.5 atmospheres. And what I end up with is V2 is equal to 350 Kelvin times 2.3 atmospheres times 17 liters, all being divided by 1.5 atmospheres times 299 Kelvin. So again, you could simplify the sides first before you start the rearranging. I just rearranged it all first. So I clearly see Kelvin and Kelvin canceling, atmospheres and atmospheres canceling, and I'm left with just my unit liters. So here I'm going to then say V2, we need to take the product, 350 times 2.3 times 17, which is 13,685 liters is the only unit left, divided by 1.5 times 299, which is 448.5. And so 13,685 divided by 448.5 is equal to 30.5 liters. So on today's assignment for gas laws, we want to be able to show the algebraic steps necessary in order to cancel units and solve for our unknown variable using the combined gas law. Again, if one variable is held constant, we just remove it from that equation, P1 times V1 over T1 equals P2 times V2 over T2, in order to solve for the variables. If you have any questions, please email me.